In this video, we're going to talk about operations with functions. We'll start by talking about addition of functions. Suppose we're given the two functions shown, and we want to determine the points in the function f plus g. Well, in order for an x value to be in the domain of f plus g, that x value must be in the domain of both the function f and the function g. Now, the only two x values in the domain of both f and g are -4 and 9. We see them there in both domains. Now, f plus g of x is equal to f of x plus g of x. And so that means f plus g of -4 will equal f at -4 plus g at -4. Okay, and that's what we have written here. Now, f at -4 is 3, and g at -4 is 17. So f of -4 plus g at -4 is 20. Well, if f plus g of -4 is equal to 20, then that means -420 is a point of the function f plus g. And similarly, f plus g of 9 will be f of 9 plus g of 9. F of 9 is 11, g of 9 is 5. So f of 9 plus g of 9 is 11 plus 5, or 16. And so the point 9, 16 is in the function f plus g. So there's only two points in that function. Now you might be thinking, well, what about f plus g of 6? If f plus g of 6 existed, then it would be equal to f of 6 plus g of 6. Well, f of 6 is -7, but g of 6 does not exist. And so you cannot add these two, so it itself doesn't exist. Now suppose we're told that f of x is 3x minus 5 and g of x is x squared plus 9x plus 7, and we want to determine f plus g of x and state the domain. Well, we know that f plus g of x will equal f of x plus g of x, which is 3x minus 5 plus x squared plus 9x plus 7, which ultimately is equal to x squared plus 12x plus 2. Now, the domain of f plus g contains all values that are in the domain of both f and g. Since the domain of both f and g is the set of all real numbers, therefore the domain of f plus g is the set of all real numbers. In other words, every real number is in the domain of f, every real number is in the domain of g, so that means every real number is in the domain of both f and every real number is in the domain of f plus g. Now, this question's not asking us to determine the function f plus g, it's asking us to determine the domain of the function f plus g. Well, f of x equals 1 over x minus 7. We know from past experience that any x value can be inputted to that rational expression with the exception of 7. X cannot equal 7. You can think of that as a vertical asymptote graphing wise, or you can think of it as a restriction when you talk about restrictions in rational expressions. So we see that the domain of f is simply equal to the set of all x element of the reals such that x cannot equal 7. Now, similarly, we see that the domain of g, we can look at it graphing wise, or we can look at it algebraically. If we look at it algebraically, we realize anything that you input to a square root function must be greater than or equal to 0. So if x plus 3 must be greater than or equal to 0, then x must be greater than or equal to -3. So we can say just by looking that the domain of g will be any real number such that x is greater than or equal to -3. Okay? So we put those two statements down. Now, the domain of f plus g is the intersection of these two. It says functions, it should actually say domains. Okay? In other words, the domain of f plus g contains every value that is in both domains. So how do you show the intersection of two domains like this? Well, some people find it helpful to draw a number line representation of each domain. Then they can visually see which values are in both domains. So the first domain was x cannot equal 7, but x is an element of the reals. That's shown here. The second domain was x is an element of the reals and x is greater than or equal to -3, and that's shown here. We want to make a third number line in which we color in every single value that's been shaded in both number lines. Well, if we were to do this roughly, we'd see every value from -3 over to the right has been shaded in both number lines, except 7 has not. 7 is still an open circle, but then every number to the right of 7 has been shaded in both. And so we can show that in green, as you see there. Okay, now we can express the domain by looking at the values of x in both domain F and domain G. In other words, the domain of F plus G is the intersection of the two domains. An equivalent way of saying this is as you see it on your screen. The symbol being pointed at means intersection. Any number in the intersection of two sets is a number that's in both sets. And so if we were to write that green number line set, if we were to write it in set notation, we would say, well, the first portion is telling us that -3 is less than or equal to x is less than 7. And the second portion is telling us x is greater than 7. But on the other hand, if we were to look at it using interval notation, we would say, well, we have numbers in between -3 and 7. We also have numbers in between 7 and infinity. Okay? And so any number in the intersection will be a number that's in the union of the two intervals shown. Now, what if we want to subtract functions? Very similar to when we add functions. Let's start with the exact same two functions we began our analysis with when we talked about addition. We want to determine the points in the function f minus g. Well, just like with addition, we realize the only two values in the domain of both are -4 and 9. So f minus g of -4 will be equal to f of -4 minus g of -4, which is 3 minus 17, which is -14. So that means -4, -14 will be in the function f minus g. And f minus g of 9 will be f of 9, which is 11, minus g of 9, which is 5. 11 minus 5 is 6. And so we can say that the point 9, 6 is in the function f minus g. And so we can say that f minus g is equal to the function shown. Now, if we're shown the two functions there, and these are the same two functions that were shown in our second example in the addition section, we would say, well, simply put, f minus g of x is f of x minus g of x. Now, when we subtract g of x, we make sure to put a bracket around it like we do here, and then we make sure to distribute that minus sign. That's a really important point here. And we get 3x minus 5 minus x squared minus 9x minus 7, which ultimately equals -x squared minus 6x minus 12. Now, the domain of f minus g will contain all the values in the domain of both f and g. And since the domain of both f and g is the set of all real numbers, therefore the domain of f minus g will be the set of all real numbers. Again, that was the same analysis as we did when we were talking about f plus g. And finally, we're going to look at the same analysis again for this question, where we determine the domain of the function f minus g given the two functions shown. So this answer is actually identical to the one in the third example under the addition section. Because they're not asking us to determine the function f minus g, they're just asking us to determine the domain of the function f minus g. So the analysis for determining the domain of the function f minus g is identical to the analysis for determining the domain of the function f plus g. And as we'll see in a few minutes, it's the same as the analysis for determining the domain of f times g. But just to refresh your memory of what that analysis is, the domain of f is x element of the reals such that x cannot equal 7. The domain of g is x element of the reals such that x is greater than or equal to -3. The domain of f minus g is the intersection of those two functions. So we can put them on a couple of number lines, and then we can make the green number line to show That intersection in green are all the points that are in both red intervals of the first two lines. And now if we want to state though that green shaded portion in either set notation or interval notation, we can. And we get the exact same answer we had a few minutes ago when we talked about the domain of the function f plus g. Okay? Now, we'll talk about multiplication of functions. And once again, it's going to be a very similar process. We'll start again with the exact same example we had for both addition and subtraction. We want to determine the points in the function f times g. Well, in order for an x value to be in the domain of f times g, that x value must be in the domain of both the function f and the function g. And once again, the only two values there are the -4 and the +9. Well, f times g of -4 will equal f of -4 times g of -4. 3 times 17 is 51, so the point -4 comma 51 is in the function f times g. And f times g of 9 will be f of 9 times g of 9. F of 9 is 11, g of 9 is 5, and we're going to get 55 as our answer. So the point 955 is in the function f times g. And so the function f times g is really just the set of the 2 points, -4 comma 51 and 9 comma 55. Now, what if we're told that f of x is 3x minus 5 and g of x is x squared plus 9x plus 7, and we want to determine the function f times g of x and state the domain? Well, again, just like we did when we saw this with f plus g of x and f minus g of x, we were using the same two functions. To determine f times g of x, we're literally just going to multiply those two functions. So we're going to say 3x minus 5 is being multiplied as a quantity with x squared plus 9x plus 7. We're going to use the distributive property. And when we collect like terms, we're going to get the function 3x cubed plus 22x squared minus 24x minus 35. Now, the domain of f times g will contain values in the domain of both f and g. And since the domain of f is the set of all real numbers and the domain of g is the set of all real numbers, then all real numbers are in both. So the domain of f times g will be the set of all real numbers. And finally, let's do this question, which we've actually done literally identically 2 other times. This time we'll do it with multiplication. They're not asking us to determine the function f times g, they're asking us to determine the domain of the function f times g. So we're just going to, as we've already done twice before, determine the intersection of the domains of these two functions. Well, as we've already explained a couple of times, the domain of the function f of x is x cannot equal 7. The domain of the function g of x is x must be greater than or equal to -3. And the domain of f times g, just like the domain of f plus g and the domain of f minus g, will be the intersection of those two domains. We should be saying domains there. So in other words, any value in both domains will be in the domain of f times g. And as we've already seen a couple of times, we're doing the same analysis again. The domain of f is the top line, the domain of g is the bottom line. The domain of the intersection is the green line. And so that green shaded portions will represent the domain of f times g. One more time, that symbol means intersection. Any number in the intersection of the two sets will be in both sets. So any number in the intersection of the two domains will be in the domain and of f times g. And so we can say, as we've already expressed once or twice before, the first portion is -3 less than or equal to x less than 7. The second portion is x greater than 7. Putting them together in set notation gives us the expression you see there. Or down below, we see we could use interval notation and say the interval from -3 to 7, including -3 but not 7, as well as the intersection, as well as the interval between 7 and infinity, not including either of those. That union between those two intervals will represent the intersection of the two domains that we've since erased. Okay. Now, with division of functions, there is one difference. So we'll start in a very similar way. Suppose we're given f and g as shown. We want to determine the points in the function f divided by g. And again, just like before, we'll look for points that we'll look for x values in both domains. And once again, we see that those values are -4 and 9. Now, f divided by g of -4 will equal f of -4 divided by g of -4. So that'll be 3 divided by 17. So it'll be 3 over 17. So the point -4 comma 3 over 17 will be in the function f divided by g. And finally, divided by g of 9 will equal f of 9 divided by g of 9, which is 11 divided by 5, which is 11 over 5. And so these 2 points will be in the function f divided by g. The one difference about this over the other ones, let's just pretend for a second that instead of this point down here, the one I'm circling, instead of the point in G being 9, 5, suppose that point was 9, 0. When we then went to say f divided by g of 9, we would be saying f of 9 divided by g of 9, which would equal 11 divided by 0, which would not exist. So if that was the case, if this point that I'm circling boldly in red had been 9, 0 instead, then the point, there would be no point in f divided by g of x with an x value of 9. Because you can't divide if the denominator equals 0. You can divide if the numerator equals 0, but you cannot divide if the denominator equals 0. So that's the one fundamental difference when talking about division of functions over the philosophies of addition, subtraction, or multiplication of functions. So let's try another one. Suppose we're told f of x is 3x minus 5 and g of x is x squared plus 9x plus 7. Suppose we want to determine f divided by g of x. Okay, well, f divided by g of x is f of x divided by g of x, which is equal to this expression right here. And we have to remember, though, that we can't divide by 0. So our domain for f divided by g of x will be all values in the intersection of the domains of f and g, just like before, as well take out from the domain of g any value that makes g of x equal 0. So to show you what that means here, we see, and it's actually common sense, we see x squared plus 9x plus 7 in the denominator. Well, we cannot include in the domain of f of x divided by g of x a value of x that makes the denominator equal 0, because we know any fraction with a denominator equal to 0 is undefined. So what we have to do is find out what values of x make x squared plus 9x plus 7 equal to 0. Well, those values are -9 minus the square root of 53 all over 2, and -9 plus root 53 plus the square root of 53 all over 2. In other words, the intersection of the first domain with the intersection of the second domain gave us the set of all x element of the reals, but we had to pull out any value of x that made the denominator, which in this case was g of x, equal 0. Okay, which is very similar to what you learned. It's actually just another way of saying the same thing that you already knew. The denominator of a fraction can't equal 0. And now what if we want to determine the domain of the function f divided by g, where f of x is 1 over x minus 7 and g of x is the square root of x plus 3? Well, let's take a look at that. As we already know, the domain of f is x element of the real such that x cannot equal 7. The domain of g is the set of all x element of the real such that x is greater than or equal to -3. So we'll go through the same process that you've already seen here. The domain of f divided by g will be equal to the intersection of those two domains. And you can see it in green right there. And that, on first glance, what you see in green is the domain of f divided by g. However, here's a big point which makes division different. Because we're dealing with division, we have to eliminate any values of x that make g of x equal 0. The only value of x that makes g of x equal 0 is x equals -3, right there. X equaling -3 would make g of x equal 0. Therefore, we have to remove x equals -3 from the domain of f divided by g because it doesn't belong there. And so we can pull it out and we put an open circle there. And so again, intersection of the two domains, just like with addition, subtraction, or multiplication, but also pull out any x value that makes the bottom function, the one being divided by, that makes that equal 0. And that actually totally makes sense. Just think about it for a sec. If we were to write f divided by g of x, given the information you see, you'd say, okay, that's f of x divided by g of x. And then you would say that's 1 over x minus 7 divided by the square root of x plus 3. And then right away, your fraction work from earlier grades would say, but wait a second, that can't equal 0. And since that can't equal 0, any x value that makes it equal 0 can't be in the domain, which in this case is an x value of -3, which explains why we're putting an open circle there. So there's different ways of looking at this. This is actually stuff you already knew, but we're using new terminology for it, and it's important for you to know how to think of it with this new terminology. Okay, and so putting it in set notation, instead of saying -3 less than or equal to x less than 7, the way we had with previous questions, we don't put that, we just put this. And instead of saying -3 to 7 with a square bracket on the -3, we don't do that, we put this. The other part remains the same. Okay. So, in summary, when determining the domain of f plus g or f minus g or f times g, we look at the intersection of the domains of f and g. When determining the domain of f divided by g, we look at the intersection of the domains of f and g, but we also have to remove from the domain any values of x that make g of x equal 0.